Okay, so let's get started. We'll start with a couple announcements. There is a lablet out, I think is due today. I'm not mistaken. Is that today or tomorrow? I don't remember. Tomorrow. Okay, tomorrow. Whatever they told you is the day, not what I just said here. Okay. Then the TAs have made a bonus lablet, which is entirely optional. Okay, we'll give it out today. It's on scheduling. They made it, not me. And if you decide to submit it, you get a bonus lablet point. Okay, whatever the each lablet gives, this will give you an extra. It's not a lot, but some people have been asking for a little bit extra work, so we'll hand that out. If you have time, do it. If not, it's optional. It's completely up to you. All right. And we have 3 more lectures to go. Okay. And then the exam is going to be next Friday. All right. A week from this Friday. That's the final exam schedule. And it is at 1 o'clock, not an evening exam. I'll send an email about this, but I just wanted to mention the final exam schedule decided by university, not by me. So that's the slot they assign to every class that's held on Monday, Wednesdays at 2:30. So we will have the exam on Friday, May 19th. It's going to be at 1. I'll send the room number. It's in Marcus Hall somewhere. Don't remember the room number. Okay? But the more important thing I wanted to mention are that everything from midterm 2 onwards is on the exam. You don't have to worry about what we covered on midterms 1 and 2. Okay? Initially, I had said it's comprehensive. I decided not to make it comprehensive, just to reduce the amount of work you have to do to study for it. And already you have been tested on that material. So it's not comprehensive. 16, lecture 16 and on, okay, through whatever we do next week. That will be on the test. All right. Again, closed book, closed notes, like everything else we have had. All right. Okay. Any questions on that? All right. So what we'll do today is 2 or 3 slides from the NFS discussion. I'm going to finish that quickly, and then we'll talk about 4 different file systems today. And of course, it won't be in as much detail as NSF, not NSF, NFS, excuse me, as NFS, because that one we spent a lot of time trying to understand how it works and so on. Right? Okay. So we were talking about consistency of NFS clients, and I said that NFS has a very weak consistency model. Whenever a client application user modifies a file, it just gets returned to the cache at the client machine, and then at some later time, up to 30 seconds later, the client might decide to send the changes to the server. So in the meantime, if the server sees a request for that exact file from some other user, it will stir stale content. Okay? So it's a weak consistency model. Now, the file system also supports this concept of delegation as part of caching. It says that the idea of delegation is, rather than caching the content, some portion of the file at the client, let's just send the entire file when you open that file. Okay? And then the client is going to hold the master copy of the file, and it can make changes to that file, and then it can then send the entire file back. Okay? If you remember last time I was talking about the upload download model for a file system, where I said there is one model where when you open the file, the server is going to send that entire file over. Then the client actually has the master copy. You can make local changes, send it back. The same thing is true here. So you have an NFS client, NFS server. You open the file, okay, and then the client is going to send a request to the server saying, I want to open the file. So the server in this case has the option. It can say, rather than just sending you whatever you want to read or write, I'm going to delegate the entire file, which means that you take a copy and then you send it over. So there's now a local copy. Okay? And then now the client IO accesses are local. They don't actually have to involve the server at all. Okay? In this case, there's no consistency problem because there's only one copy which is now at the client. So you're just writing here too. Okay? Now, if it turns out that some other machine tries to open the file, okay, then the file is now resident at the client, not at the server. The server can't serve that file anymore. Okay? So if that happens, you have to recall the delegation. So you have to tell the client saying, okay, give me the file back. we'll go back to the old mode where all requests have to be sent to the server. Okay, so you'll recall the delegation. The client is going to return the updated version of the file. So now you go back to the old model where multiple clients can access that file just by sending read or write requests to the server. Yes, question. Okay, question is, when does the server decide to delegate the file? So this, first of all, this feature is only present in version 4 of the NFS file system, not in version 3, because this is a stateful feature. You have to keep track of which clients have what file delegation. So it's stateful, so you can only do it in version 4. But the question is, when do you decide to delegate? Okay? So it's always a good idea to delegate if the server believes that that machine is the only one going to access the file. Okay? If it thinks that this file is going to be accessed by multiple machines, then you shouldn't delegate. You should have all the requests come to the server so that the server can serve all of the client. Because in delegation, you are basically telling the client, temporarily you are the server for this file. You take it over and you manage it. Okay? So the server does not actually own the file, the latest version of it at least doesn't own it. So you can't actually serve a second client this way. Okay? So the short answer to this question is, first of all, it's an implementation detail, but the way it should work is if the file maybe has had a history of just having one client accessing it over and over again, then you delegate it, right? Good examples are maybe files in your home directory are worth delegating because most likely you are the one accessing them. But maybe files that are binaries of application programs, you don't delegate, you just serve them from the server because multiple users might access those files. Yes, question. Yeah, that's a good question. The question is there a way to periodically update the server? Because what if the client fails and then the copy that you updated is all gone, right? So that's again an implementation detail. So so long as it's delegated, you can still update the server, but you still hold the master copy. That can be done just to avoid that exact problem that you mentioned. Okay, so you could still continue to flush in the background every so often, but you still hold the master copy, right? Okay, that's delegation. And then there are a few other details. One of them is what happens when the RPC request between the client and the server fail. Right? Remember when we were talking about RPCs, we said requests might fail and so on. Just the first thing to realize is if RPCs are being used over TCP, there's no failure that the application needs to worry about. In this case, the application is the client and the server, because TCP will take care of retransmissions for you. You don't worry about it. You just send a packet on a socket, it's going to appear at the other end. It may have to be retransmitted a few times by TCP if the network has dropped that packet. Okay, so this is only true if you are running RPC or UDP, okay? Because UDP is not going to give you packet loss recovery, all of those features. So now, if you do that, the client and the server actually have to deal with lost requests or lost replies and so on. Okay? So here is how it's going to work. Every RPC request is going to have an ID, a numeric ID, which is unique. Okay? So you will see that there's request number 1, 2, 3, 4 that has actually gone from the client to the server. Okay? So in this case, we will assume that the server actually received the request, it processed it, but the reply got lost. Okay? So you never heard back on your RPC request. Okay? So the client is going to time out and then resend the request. Okay? Because TCP is not timing out here. So client has to time out and say, I send this request again. Okay? So now, if you actually go and process that request again at the server, you're going to have a problem. Okay? Suppose the request was, I am appending a string to this file. Okay? You sent it to the server appended that string to the file, you didn't get a reply. So you retransmit saying append this string to the file. Okay? You will see that the request is now not idempotent, because if you actually execute the request twice, your file contents are incorrect because you actually send that request once, but the server has executed it twice. So you cannot do that. Okay? So somehow there has to be a mechanism for the server to figure out if the requests that are coming in, the NFS requests, the reads and the writes, have already been seen before and have been executed. Okay? So that you don't execute the bucket. That's the only way you are going to make this entire operation idempotent. Okay? Yes, your question. Okay, question is, what is the utility of doing this over TCP? There are any number of reasons why you might use UDP on local area networks. One of them is efficiency. TCP has a three-way handshake, if you remember. Every RPC request is going to have to send 3 messages before you can send the actual request. In this case, you just open a UDP socket and send, right? So on local area networks where probability of loss is low, okay, you can use UDP. Okay? On a wide area network, you would never want to do this. Or if your LAN is noisy and it has lots of lost packets, you want to switch to TCP. Okay? NFS can support both. It has no problem. But if you use UDP, it's going to have this additional feature where the application can do loss recovery, not the network. Okay? So how are we going to assume that the request is idempotent? So what you do is you keep a request cache, okay, which is shown in this picture. Every time you execute a request, you keep a copy in the cache saying this request came in, this was the reply that was generated. Okay? So the request ID, the request itself, and the reply. So you log that in the cache. Okay? So now when a request comes to you again, you have to first look in the cache saying, have I already seen request 1, 2, 3, 4? Okay? In this case, because the request was already received and executed, there will be a copy in the cache. Okay? So if you have a cache hit, you're not going to execute it again. Instead, you just go to the cache, you take the reply that was generated, which is also logged, and you just send the reply. Okay? Because the client is just wanting the reply. Okay? So you'll just fetch it from the cache and you'll send it back. You won't actually execute it again. Right? So you should see different cases where here the reply is lost, and then you send this and you get to the cache and you get it back. Right? So you can have all these issues that you have to deal with if you're doing application level loss recovery. You can't double execute a request, okay, especially if it's going to cause problems at the server. Right? Yes. Okay. Question is, for how long does the reply stay in the cache? That's an implementation detail. Yes, you can decide that it's a 1 hour cache or something. You are not going to have clients that are going to keep trying for 1 hour. They'll, after some number of retries, the client will assume the server is down, that it is not responding, and it will just stop. Right? So you don't have to keep a very large cache, but it can't be 1 second, because you might have an outage for some number of seconds. So hours is probably the right way to think about it. Right? Yes, question. Is this specific to the older version of NFS? Is that the question? So this is there in all the versions, right? So this is not specific to any new versions, because the very first version, NFS v1, there was no RPC or TCP. RPC started over UDP. So they implemented this way back when you had the very first version, and it has continued since then. More modern versions use TCP, so you actually don't see this problem. Okay? Even though you may have a request cache, TCP will ensure that you are not sending duplicate requests to begin with. Okay? Even though packets are being retransmitted, the application only sees one request, which is the one that it received eventually. Okay? Yes, question. The question is, do we need this cache only if you want the request to be idempotent? That's exactly right. If the requests themselves did not cause this idempotency problem, you could execute them multiple times. There's no problem, right? So that's not an issue. So if you are just sending a computation saying, here, take this data, find the average and send it back, you don't need, you can execute it again. In this case, because you're making changes to files, that's a problem if you execute it, right? So that's why you need it. Any other questions? All right. So that's essentially our RPC mechanism to deal with failures. As far as security is concerned, versions 1, 2, and 3 of the file system used a very simple security model. Every request goes with a user ID, that's the ID of the user, and a group ID. Okay? So the server is going to just look at that user ID, group ID, see if you have file permissions. If so, you access it. If not, you don't let the client access it. Okay? This is done using the lookup request. Okay? Now the problem is, although this allows you to make sure only users who have the right permissions on the file can access the file. Okay? So you're not allowing unauthorized users with different user IDs to access the file. You still don't have a secure channel between the client and the server. So your entire NFS traffic is going on your LAN unencrypted. Okay? So if you're accessing a sensitive file, You say I read the file, the entire file is coming as an RPC request. The contents of the RPC request have actually all the contents of the file. So if an adversary intercepts network traffic, they can actually read the contents of all the files or see what writes are being made to all of the files, because the network is not encrypting the traffic. All you're doing is to make sure that users who are accessing the files can access it only if you have the right permission on the file. Okay. The same in HTTP versus HTTPS, by the way. If you use HTTP and you try to log into some site, okay, your username and password is going to go as an HTTP request, which is unencrypted. Okay. So anyone who actually can see this request on the network can see your username and password. But if you use HTTPS, okay, HTTP will encrypt everything that you're sending. So then when you log in and type in your username, password, it actually goes encrypted. Okay? Same problem is there in NFS as of version 3, but as of version 4, just as HTTP has the secure HTTP, which is HTTPS, so does NFS. So it introduces notion of a secure RPC. Okay? So it's like an RPC request, but everything you're sending automatically is encrypted by the RPC layer. The RPC runtime stub is going to take all of your requests and is going to send it to the security layer. It will encrypt it. You'll send it here. You will decrypt it and then send it to the stub. So everything is now encrypted. So you can't actually read file contents on the network, which is, of course, a security problem. Okay. Next question.
My question is based on the server
Okay. So that's a good question. Question is, in the previous case, I said the client actually can send a user ID and a group ID to the server. How does the server know it is authentic? Right. So the first thing is the server trusts the operating system on the client. So if the client is sending a user ID, it actually comes from the client, not from the user. Okay. Now, if you don't assume that you can trust the OS, then all bets are off, because the client OS, you can hack the OS and send whatever user ID you want and get access to other files. Right. So that problem exists, because the authentication mechanism is whatever the client tells me is the user ID, I believe. Okay. If you don't have that trust model, then this is not going to work. You will let some malicious OS get access to files. Okay. All right. That's secure RPC. NFS also has the notion of replica servers. I'm not going to go into this because the next file system has a lot more replication. So here we have assumed that NFS has one server that has some files. Clients can access those files. You can have another server having a different set of files. You can access as many servers as you want, each serving a different set of files and directories. Okay. Version 4 allows those files to be replicated. Okay. So you have the entire file system is replicated, and then you can make a request for any of the file from any of the replicas. Of course, now NFS has to keep all the replicas consistent, which is another headache, because if you see a write and one replica, it has to be sent to all of the other replica. So that has to be then implemented by the NFS server. Okay. But I'll not say much more about replication, because we'll go to the next file system and we'll see a lot more of this in that file system. Okay. So as I said, today we are going to look at least 3 or 4 different file systems. We'll start with Coda and we'll look at xFS. In that context, we'll look at RAID and log structured file system. Let's say some very brief things about Hadoop file system, HDFS, and Google file system, which are somewhat similar, GFS. And then we'll end with object storage system, which is not really a file system at all, but something you should know, given that you have some knowledge of what cloud systems do. Okay? But let's start with Coda. A very old file system designed in the 90s. Okay. What's different about this file system? So this file system was specifically designed for mobile computing. Okay. So the assumption here is that the clients are mobile devices. Okay. In those days, there were laptops. Even today, you have laptops, but you have all kinds of other devices. Okay. And then the question is, what should the file system implement to better support mobile clients? So your question should be, how is a mobile client different from a wired desktop? Okay, what differences do you think exist? Yes.
There's an issue of power, battery.
Okay, you have battery. Okay, energy constraints. Anything else? Yes. Okay, so you're not always connected, right? So first of all, client devices are more resource constrained than maybe desktop. Not anymore. Your laptop actually has 816 cores. Maybe your desktop is similar, but in those days, at least it was true. Okay, but the bigger problem is in the mobile computing world, you cannot assume your device is always connected. First of all, it will be connected to wireless network. Wireless network will change over time. I can shut my laptop and take a bus to go home. At that point in time, the device is not connected. Okay, if a file changes, you can't receive notifications from the server, even if you want to implement consistency, right? So this is called a weakly connected environment, right? Where disconnections are common. Okay? So how do you design your file system in a world where clients are weakly connected, which means that they might go offline for some part of the time, not all the time. It's not a failure. You just essentially disconnected from the network. Maybe you took a plane ride, you went on a bus, you just might have shut your laptop down because you're not working, and then you reconnect after some time, maybe from a different network. Okay? So how do you deal with this? Okay? So that's the basic premise for Coda, saying you need better support for these clients. Okay? So what we will do is to see how you can actually use this notion of aggressive caching to deal with this notion of disconnection. Okay? So you should think of this from two perspectives. Okay? How should the client be different and how should the server be different? Let's start with the client. Okay? The client is what the user is using. Okay? Now, if from a user's perspective, you want to give them a similar experience as if they are always connected. Okay? So maybe you shut your laptop and take a plane ride. Normally, you assume that you are not connected, so you will assume your files on the server are not accessible. In Coda, the files are actually cached, so it just looks like you're always connected, even though there's no server actually present at that point. Okay? So the user can continue to work as if nothing has happened. Okay? And then when you reconnect, all your files are sent. Okay? If you use things like webmail or Gmail, it has an offline mode, okay, where it caches your data. This is basically where this idea came from. Okay? So they essentially have an aggressive cache where even if you're disconnected or offline, your most access files are always with you. Okay? You don't have to do anything specific to copy files to take it with you. Okay? Normally, you would manually say, I need to work on this file. I'm going to make a copy and take it. The file system is doing all of that for you. So the file system looks like it's always connected, even though you may actually be disconnected. Okay? So, and then you still have to deal with consistency because you might be disconnected. Then what are you going to do? So we'll see how all of that works. Okay? But you have the basic idea of what the client has to do, which is this aggressive notion of connection. Okay? So here is some details before we go into higher level concepts again. So first thing is each file in the Coda file system belongs to a volume. A volume could be a disk or a partition of a disk. Okay? The volume can be replicated. Okay? So you will see that you essentially have the two copies of the file server. Each has copy of the entire file. So that way, even if the server goes down, your machine, the copy of your files are still available on another machine. Okay? And if the client gets disconnected, a copy of your files are on your machine. Okay? So you have identifiers which include the volume ID and the file handle. The way you go access it is you say the machine name or the server name and the file name. That's how you access these files. Okay? Now here is an example of server replication and what can happen when there are consistency problems because of network failure. So here's the scenario. Okay? There are three servers. These are the machines with disk S1, S2, and S3. Okay? There are two clients, client A and client B. Okay? Let's assume that they're accessing the same file. Okay? Clients A and B have opened the same file foo. Okay? Now, when the network is connected, okay, meaning all of these machines are all connected to one another, when A makes a change, it sends it to one of the servers. The server will broadcast the change so the other server see it. And when B makes the change, same things happen. So the servers are keeping the copy consistent with one another. Okay? Now let's assume that the network gets partitioned, okay, which means that the network breaks. Okay? So now you have two parts of the network. In the left half, S1, S2, and A are connected to each other because that part of the network is intact. And on the right half, B and S3 are connected to one another. Okay? Now, from A and B's perspective, they don't know that there's a network partition. So A is going to continue to make changes to the file. Okay? And so is B. Okay? Now, when A and B make changes, the servers in the two halves can't communicate with one another. So they cannot actually keep the file consistent anymore. So the file is going to start diverging because my changes are not visible to the other client and their changes are not visible to me. Okay. So now when the network partition is fixed, the servers are going to try to address these issues. Now, if some files are only changed in one partition, not the other, you just send the changes over and everything is fine, right? Because if you only one of the two clients has changed the file, then the servers can send that update to the other server that didn't see it and we are good. The problem arises if both clients change the same file. Okay, so this is going to be a write-write conflict. Okay? So when you try to merge it or synchronize these changes, you will not be able to synchronize this because you don't know which copy is the more authoritative one. Because you wrote something to the file, maybe your friend wrote something to the file, you can't just overwrite each other's changes. Okay? So this is very similar to when you have a Git conflict or something like that, when multiple users change the same file or the same line of the file, you are going to essentially get a conflict. Okay? The way you resolve this is manually. Okay? Git is going to throw a conflict message and then you are supposed to resolve it manually. The same is true here. Okay? The system is going to say that there is a conflict in this file and ask the user to figure out what to do. The system doesn't know what to do, right? But the issue is, how does the system know that the file has changed to begin with, or there is a write-write conflict to begin with? The way you do that is you have something called a version vector. Okay? That version vector has nothing to do with a vector clock. It looks like a vector clock, but it's just a version vector. The version vector simply says what is the version number on each of the file servers that I know about. Okay? So initially, let's say that the file was at version 1. All three servers have version 1 of the file. So the version vector on the file will be 111, which means server 1 has version 1, server 2 has version 1, server 3 has version 1. Okay? Yes, question.
So the size of the version vector.
Yeah, this question is, what is the size of the version vector? The number of entries in this version vectors is the number of servers that have a replica of the file. So we're assuming the file is replicated on 3 servers. So the version vector will have 3 entries. Each of the entries will say what is the version number on that server. Okay? So we start with 111. The network is partitioned. Okay? So user A is, or client A is going to update the file. Okay? So S1 and S2 are going to update their version numbers. Okay? But they know that their 3 is not reachable. Okay? So they will update the version number to 2 to 1 because they have not yet sent their changes to the third one. Okay? So they assume that 3 still has version 1 of the file. Okay? And the same thing is going to happen on client B. Client B makes an update to the file. Yes, the server 3 will update its version number for that file, but it can't send the changes to S1 and S2. So the version number is going to be 112. Yeah, because this server will say, I have updated it to 2. So this copy of the file will have 112. The other copy of the file will have 221. Okay? Now, when the network partition is fixed, you compare the version numbers. Okay? If one vector is strictly greater than the other, that means that that half has actually seen changes that the other half has not seen. You simply send the changes over. Similar to what we had seen in vector clocks, where if the vector is strictly greater, you know that event happened later and so on. So same thing would be true here. But if the version vector show a conflict, which means some entries in one vector are greater than the other one and vice versa, you know there's a write-write conflict because the two halves have seen some changes that the others have not. So 2 to 1 and 112 will be a conflict, but neither vector is greater than the other. So this the system will flag and tell the user saying there's a problem with this file, go fix it. Okay? So that's how you're going to detect conflicts. Okay? So you are actually going to keep track of versions and then compare versions and figure out who's seen it. Is this an actual conflict or should I override the file and so on? Is this clear? Okay. So if only A had changed the file and B had not changed the file, the copy of the file on S3 would have stayed 111. Here it would have been 2 to 1. That's not a conflict. You would simply send the new version and then the file version would become 222. Okay. Yes. Question.
Say a client updates, you have the partition, client updates the file. What's it?
Yeah, the question is, if the file is updated multiple times, are you going to keep incrementing the version? And that's an implementation detail as to do you update the version on every write and so on. But for our example, let's assume you do. Okay, and that's okay. You will, if you make 2 updates, this will become 331, and that's still going to cause a conflict. Okay, because your last one is still 1, and if you make a change on the other one, that's going to conflict. So yes, you can assume that there will still be a conflict. Yes, question. Okay, question, what does manual reconciliation mean? Manual reconciliation means the user is going to be asked to manually fix the file. Exactly what you do if you get a Git conflict, okay, you are going to actually look at the differences and then you can merge it or you can throw out whatever you do, the same thing you would have to do here. Okay. All right. So here is how the client is going to work. Okay, the client essentially is in one of 3 states. Okay, you have something called the holding state, the emulation state, and the reintegration state. Holding state essentially means the client is connected to the server, and this is when it is actively downloading files into the cache, whatever it thinks the user might need based on whenever they disconnect. Okay, now you can make some predictions saying user is working in this directories, or there are 3 applications open. This one is accessing this directory, this one, or you can say, I have a 7-day history of everything you access. I'm going to make sure all of those directories are cached. Use any heuristic, okay? But based on that heuristic, the client will actively keep downloading latest versions of the file and keep it in the cache. Okay? Now, the moment you disconnect from the network, you go into emulation state. Emulation means you emulate the presence of a server even though there isn't one. Okay? So in which case, your local machine cache acts as the server. Okay? All your applications can continue to access files as if they are stored at the server. You have a copy of some branch of your directory is already cached. So it will look like your files are there as if nothing has happened. Okay? But clearly not all files are there, only the ones you cache. So it's not going to do magic for you. You suddenly decide to access some file, it hasn't cached, you'll still get an error. But if it does a reasonable job, you will not notice. Okay? Maybe your entire home directory is cached or all your email is cached. It will make some reasonable choices and then you won't see any problem. You will continue to work. Okay, your machine will be in emulation mode. And then eventually you reconnect back to the server. You go into reintegration mode. Reintegration is where you are going to send your differences or updates to the server. The server is going to send its differences to you. You are again going to use similar concept like version vectors, because who knows, somebody else could have updated the same file you updated on your laptop. Okay? So you have to still detect conflicts. Okay? Same thing I talked about on the previous slide will also hold when clients are actually making local updates and you reintegrate. Okay? But the basic idea is, assuming there are no conflicts, the laptop will send all of its changed files to the server, and then the server will then essentially send its changes, and then you go back to holding mode to see if you want to access any more files and keep them local. Okay? So you will basically cycle back between these 2 modes. Yeah, of course, before reintegration is complete, you may disconnect again, in which case you'll go back to emulation. Right? So that's your state transition model of how a Coda client is going to work. Okay, yes, question. So reintegration means you're going to send your local updates to the remote server, but if there are conflicts, you've got to also flag those conflicts and what. So you do have to check if the files have been modified at the server. Okay. Any questions on this? Okay. So as you can imagine, these ideas were developed back in the late 80s and early 90s, although Coda was never actually a big commercial success. Some of these ideas are actually present even today. If you use any cloud storage, right, Dropbox or Box or OneDrive, and if you actually have the client that's doing synchronization, it's basically doing this, right? So if you see Dropbox, a Dropbox folder is always on your machine because it's cached your entire Dropbox. And if you make changes, it's going to do exactly this. When you're disconnected, you can work on it. When you reconnect, it will upload changes, download from Dropbox server. Same is true practically for any cloud storage service. That's how most of them actually work. Whether it's Google Drive, assuming you use the client version, not the web version, it will do exactly this, right? Or OneDrive and all of these things. Okay. So with that, I'm going to say one more thing and stop. The other thing in Coda, which I didn't mention much, is the file system also implemented stronger semantics. So it actually gives you something called transactional semantics. Okay? Last time I was talking about NFS, I said you have Unix semantics, your session semantics, and you can have immutability semantics, and you can have transactional semantics. Okay? So in transactional semantics, if you make changes, okay, just as database transactions allow you to have serializable changes, the same is true here. When you open a file, you can say this is a begin transaction of file, close the file, you can say it's end transaction. If multiple clients do that, if you can make the changes serializable, you have transactional guarantees. Okay? So unless you have a conflict, of course, in which case you are going to force reconciliation, but otherwise you have a serializable operation, so you can reason about them and so on. Okay? Now, this is a much stronger semantics than most file systems will support, but because they were looking at disconnected operations, they didn't want arbitrary bad things to happen. They went and implemented transactional semantics. Normally, you wouldn't go that far. NFS doesn't have any guarantees at all. Here you are getting atomic guarantees on changes where you can undo all of the writes, go back to before the transaction and so on. Okay? So that's an additional feature. It's not directly related to mobile computing, but that's what the file system does. Right? Okay. So I'm going to skip the caching and then go to xFS, which is a different file system. Okay, we finished one, Coda, which was designed for mobile computing. Okay, distributed file system. Here's another one called xFS. Okay, the X is a small x there, and that essentially means that there is no server. That X was just a cross for saying there's no server. So this was designed as a serverless file system. Okay, there is no single server in the system. Okay, so the idea was this is a fully distributed file system, and the reason they came up with this is, if you remember when we were talking about cluster scheduling, I started with this network of workstation model and said, can we not use idle resources on all the machines? And then that way you can make use of all of the compute in your network. Okay? Same group 20 years or 15 years later decided, why not use the same idea for file system? Everybody has a powerful machine. These machines have disks. Why have a server? Why not use all the disks on all the clients and make a file system out of it? Okay? So now there is no server because you're just using some files are on some machine, some other files are on some other machine, and you just have to make use of all of the storage space and make a distributed file system out of it. Okay? That was the central idea behind xFS, which said, first of all, it removes the bottleneck of a server. Okay? Because if there are lots of clients accessing it, there's a bottleneck. That's given. Right? But if your files are distributed across all kinds of machines in the network, then the load is spread across all of these machines. Right? Now here, we will make some assumptions. We are not going to assume these machines are laptops where they randomly disappear. Okay? If you do that, then your file system will have to have high degree of redundancy and replication, similar to what P2P file systems do. Okay? If you remember in peer-to-peer, you said peers can come and go. So every piece of content is stored on multiple machines, okay, with high degree of replication sometimes to make sure even if number of clients disappear, the content remains accessible. You don't make that assumption here. We are talking about desktop clients, not laptops that just go out of the environment. So if you have desktops that are always connected and always on, similar to how we use their compute resources for scheduling, now we are going to use their storage resources for making a big file system. Okay? That's the idea. Okay? So in this case, as the name xFS suggests, it's no server. Any file can be stored on any machine. Okay? And then we'll see there are some other ideas I'm going to talk about. And you can then access those files on the server. So when you open a file, you got to figure out which of these 100 machines in my network actually has that file. Okay? So you have to keep additional metadata to figure out who has the file, where can you access it, and all of that extra information. Okay? But I'm not going to talk about those file lookups. Instead, I'm going to talk about two other concepts that are also important in xFS. The first one is essentially what is called RAID and log-based network striping, right? And the second one is log structured file system. Okay? So let me talk about RAID, which you may have heard of. I'll talk about log structured file systems. We'll put that together, and then you will see how the server actually works. Okay? So let's talk about this one at a time. Okay? First concept, RAID. Okay? RAID has nothing to do with xFS, as it turns out. It's a separate concept of how do you make a storage system out of a large number of disks. Okay? So RAID essentially is a storage system that's built on disk arrays of disks, a large number of disks. So why do we need arrays of disks? If you have lots of data to store, okay, a single disk may not be sufficient to store all of your data. Okay? Now you essentially need a multi-disk storage system because you have lots and lots of data to store. Okay? One way you're going to do this is you keep some files on disk 1, some other files on disk 2, still other files on disk 3, and then you just manage your system that way. Right? That's the standard way. This is called just a bunch of disks, okay, JBOD. Not very good, because what if some disks become full and others storage space on the others, or some files are popular, so some disks are overloaded, they see a lot of IO, others are not. Okay? So you can have all kinds of problems. So what we are going to do is take all of these disks and make one giant logical disk out of it. Okay? So from the OS and the user's perspective, they see one giant disk. They don't actually see the presence of individual disks in the system. That's called a disk array. Okay? A disk array is an abstraction where you take multiple disks, you pool them together, and you make one big disk out of it. Okay? Now, when you construct a disk array, you have to keep the reliability problem in mind, which is what I had mentioned when I talked about fault tolerance as well. Okay? So reliability of n disk is essentially the reliability of one disk over n, because the probability of any one failure is going to cause problems in your disk. Okay? So let's say you take a single disk, you buy it from, let's say, a store, and you look at its manual, it'll say it has a very high reliability, 50,000 hours before it fails. That's called the mean time to failure, MTTF. On average, that's its lifetime. Okay? So that's a lot of, that disk is going to last several years. But now if I buy 10 of them or 100 of them, then the mean time to failure of those collection of disks is, in this case, 50,000 over 70. Okay? That's 700 hours. Okay? So that's dropped from 6 years to 1 month. Okay? That means that you should expect some disks to fail every month in your system. So you bought 70 disks, okay? You built this one big file server. Next month, one disk is down. Okay? On average, not guaranteed, but that's what is actually going to happen. So if you don't keep any redundancy in your system, immediately you're going to see data loss, because your files that you stored on that disk that failed are gone, right? So you want to construct your disk arrays in a way that actually do not reduce the reliability of the system, even though you have a large number of disks. Okay? And that is where we are going to essentially get into this notion of RAID. Okay? RAID is an acronym. It stands for Redundant Array of Independent Disks, RAID. Okay? So essentially, that's what we are now going to look at. How can you now make this one large logical disk? Okay? So it has the storage space of all of your disks. Yet, even if some disks fail, you're not going to have data loss. Okay? Then you have to keep some redundant information. The question is, what are we going to do? Okay? So you want to essentially assume that availability is not compromised, even though disks have failed. Okay? But you have to keep this extra information. So what are we going to do? We'll see several different ways to do this. Okay? What's the simplest thing you can do? Sorry? Just replicate the data. So simplest thing is called mirroring. Okay? For every copy of a file, you keep an extra copy somewhere. So there is, for every disk in the system, there's a backup disk. That's the green disk. Okay? So essentially, whatever is on the black disk will also be on the green disk. Or in this case, actually, there are two disks here. That's your mirror group. Okay? So it's not, the black is not mirroring the green. The black and green on the left are being mirrored by the black and green on the right. Okay? So whenever you send a write request, the write request has to hit both disks. Every write is replicated to two disks. When you send a read request, you can send it to either disk. It doesn't matter, because both of them have the exact same copy. Okay? There's no consistency issue here because writes always hit all the copies. Okay? That's how the array is going to work, because the write request is going to come to the array driver. The array driver will set this disk as a replica here. It'll send 2 writes, wait for the replies, and then tell the client write is done. Okay? So every logical write is 2 physical writes. Reads, you can go to either one. Okay? Simple approach. Okay? You now can deal with disk failures. You can deal with one disk failing for every mirror group. Okay? But now what has happened is you essentially cut your storage capacity in half. Okay? You bought 100 disks, but it can only use 50 disks, but other 50 disks are backups. Okay? So you spend a lot of money, but half of your money is gone into making sure there are no problems because of disk failures. Okay? So that's a high price to pay. So we are going to try to do better than that. This is called RAID 1. RAID level 1. RAIDs come in levels. Okay, RAID 0 means there is no replication. So if something fails, the data is gone. RAID 1 means you are going to do mirroring. Okay? You're not going to look at RAID 2 and RAID 3. You'll jump directly to RAID 4. Okay? So how are we going to reduce the overhead here? Okay, so let's talk about how to make sure you can tolerate disk failures but not have this problem. So here are 5 disks. Okay? The green disk in this case is going to serve as a backup for these 4 other disks. Okay? But we are not going to make an actual copy, which we did in mirroring. We'll do something better than that. Okay? In this case, let's assume that you have 4 blocks here, D0, D1, D2, D3. Okay? You take these 4 data blocks, okay? You XOR those blocks, and you get a new block, which is called the parity block. Okay? And that parity block you're going to store there. Okay? So P, in this case, that block P on the green disk is D0 XOR D1 XOR D2 XOR D3. Okay? So the system is going to essentially do an XOR operation and store that parity block. Okay? So you might say, what does this give us? Okay? So we are going to use the XOR operation to figure out what can this give us. Yes, you have something to say. Yeah, go ahead, answer. Yes, you are assuming only one disk will fail at a time. And then the question is, what can you do with that? How can you reconstruct what is on that disk? Yeah, so here we are going to, I hope you know what at least XOR means, right? So this is a bit operation, right? So here we'll use the property of XOR, which is A XOR B is C. Okay. So if you have this, then you will know that A XOR C gives you back B, and C XOR B is going to give us back A. That's the property of XOR. You can just look at the bit table and actually convince yourself that you take 2 elements and do an XOR and get a third element, you can substitute that element for one of these other 2 and get back the other. Okay? And this is going to be true for any number of XOR. So if you have A XOR B XOR C is equal to D, D can be replaced for A, B, or C, and it will give you back. Right? So how are we going to use this? So what we will do, okay, is let's say this first disk fails, as is gone. Okay? And then the client comes and says, give me block D0 for my file. Okay? D0 is no longer accessible, but you are going to reconstruct it on the fly, because what you're going to do is you're going to actually read all the other blocks, D1, D2, D3, and P. You're going to XOR them, and that's going to give you back D0. So you'll reconstruct it on the fly because you no longer have it. Right? So you can still continue to serve requests for data on the failed disk. It just costs more, because rather than just going and reading that one block, I've read all these other blocks and I have to do an XOR on top of that to get the block. But I can still do it. Right? So this is going to be a reconstruction operation. Right? So let's talk a little bit. So that's basically our property. Okay? So you essentially do D0 to D3, you get that parity block. So that means that if D0 fails, I'm going to essentially just get all the rest and get my block. Okay? So this is called RAID 4. Okay? Now what did this give us? The amount of redundancy has decreased from 50% to 1 over n, where n is the size of my parity group. So here, if I buy 5 disks, okay, I only keep one disk for keeping extra information. That's my parity. All these other data is actual disk block. So instead of cutting my storage capacity in half, I cut it by 1 over n, okay, where n is the size of my parity group. Okay. That's more advantageous because I don't have to spend as much money to protect my disk. Each disk is protecting now a group of disks. Okay. Clearly, if 2 disks fail, we can't do anything. Okay. So this can tolerate a single disk failure, not 2 disk failure. That requires additional schemes. Okay. So the first thing. Okay. Now the other thing I'll say is how are files going to be stored on this system? You use what is a concept called striping. Okay. Striping essentially says that you take a file, you chop it into blocks, and you store those blocks in round robin order. Okay. So if I have 7 blocks of my file, I'm going to take block D0, store it on this disk. D1 goes here, D2 goes here, D3 goes here. That one you can't do anything. That's parity. I cycle back D4, D5, D6, D7. Okay. So blocks of a file are stored on disks in round robin order. This is called striping. Okay. You could have said, I put file 1 on this disk, file 2 on some other disk, and so on. That's not what you do. Okay. Every file is now stored on all the disks. Rather than taking a file, normally you would keep it on one disk on one file system. No longer true. Okay. Files are all striped across all the disks. Okay. What does this give us? Why would you do this? Yes.
Even modular files.
So first thing, as is being pointed out, is you get better parallelism and load balance. First thing is you'll get parallelism. Okay? Because remember, from outside the system, this just looks like one giant disk. Okay? So if I now say get me the entire file, I just send requests in parallel and all the disks are working to give me the file rather than going to one disk and getting it. So essentially it is like a parallel disk system where each request for the more than one block of a file can be serviced in parallel. So I may have higher throughput. That's number one. Okay? Second, as what was mentioned here, was you'll get better load balancing, because maybe if you had not done this, you had kept entire files on disk, there will be disk imbalance. Some disks might see more workload than the other. Okay? Some disks might be underutilized. You don't control it. Here, every file is stored on all the disks, so I don't need to worry which disk is popular, which file is popular, which one is not. Popular files will served by all the disks. Okay? An unpopular file will still be served by all the disks. Yes, question. Okay, question is where is the information about which files are on which disk? The thing you want to keep in mind is this entire thing, right, is going to look like one big disk here. Okay? From the outside, this is going to look like one big disk. You don't actually see the presence of this disk. So this disk, this big logical disk, is just accessed as a linear block. So you say block 0, block 1, block 2, block 3. Okay? And then internally, the hardware controller for this array is going to go and say block 0 of this logical disk is that block. Block 1 of that logical disk is this block, and block 2 is here, and so on. So it's going to do the striping for you. So you don't need to keep track of my first block is on disk 1 and location X. My second block of the file is on this other disk location Y, because you don't even see the presence of these disks. Okay? This just looks like one normal disk to you. Okay? It's just that internally it's multiple disks that are serving whatever you're doing. Okay? You still have to keep track of where your blocks are stored on that logical disk. That's done in your inode. We talked about inodes a couple of lectures back. So that metadata will tell you which blocks blocks of the file are stored where, but you don't need to keep an additional mapping of which disks store what blocks. That is done logically for you. Okay? Question there. Yes. Okay, question is the cost of accessing files is going to increase because you are now querying all the disks. That's the question, right? So if you think about it, there are two ways to access a file, block by block or entire file. Right? If I access a single block, say give me one block, that's going to be a request to some disk. That's not different if the entire file was stored on one disk, you'll still get that. Okay? If I say give me the entire file, okay, In this case, the file system will make 8 requests. Say, give me D0, give me D1, give me D2, and so on. If you had kept that entire file on a single disk, that would have resulted in 8 requests to that one disk, which it would serve one at a time. Okay? Here, those 8 requests are spread across 4 disks, so each disk is serving 2 requests. Right? So your requests are spreading out across disks, but presumably that's a good thing, not a bad thing, because you will see that it will be faster to serve 2 requests per disk than serving all 8 requests from one disk, because then you are getting parallelism in this case. Okay. Any other questions? Okay. So there's one problem with RAID 4, which we'll talk about, and then we'll go to RAID 5, which is that in this case, you have this green disk, which is storing our redundancy information, the parity blocks. Okay. So what you will see is this parity block is actually, or parity disk rather, is actually going to become a bottleneck. Okay. Why is it a bottleneck? Because every write, no matter how small, okay, to any of the disk also has to update the parity block, because that's our definition. So if I write just one block, so I update D1. Okay. To update D1, normally if I didn't have this parity block, that would just be a write to that block and you're done. Okay. In this case, to write to D1, first I have to read D0, D2, D3 and the parity block. Okay. And then I got to insert the new version of D1. I reconstruct the parity, and then I write down D1 and P. Right? So this is called a read, modify, write cycle. Okay? A single write turns into a read of the entire parity group. Okay? Because I got to reconstruct the parity. I've updated that block. So this parity will no longer be valid if I change it. Right? So to change it, I got to read the remaining blocks. That's my read cycle. Okay, I modify that block, I insert the new block, and then I compute the parity, and then I do a write. Okay, and then essentially, so one write is going to be multiple reads, an XOR plus a write, okay, which is quite expensive. Okay, large writes, you don't need to do that. If I'm writing 4 blocks, that's very cheap, because I can simply take those 4 blocks at a time, compute the parity, and just override. Okay, because all the blocks are getting overwritten. I don't need to read anything to recompute. But if small writes, I got to read the remaining blocks. Okay, that's the first problem. Okay, so small writes are essentially going to become a bottleneck. The second problem is a write to any of these disks is also a write to the parity block for that group. So the parity disk, the write load on the parity disk is going to be equal to the sum of the write load on all the remaining disks, because every write on any disk always updates the parity block. Okay, so if I have one write here, one write here, one write here, and one write here, there will be 4 writes there, because all those 4 parity blocks corresponding to each block updated are also being updated. Okay, so the parity disk is going to have a very high load as a result of this. Okay, is that clear? Okay, so what do we do? Okay, we want to keep the parity, but this is not going to really work. Yes. Yeah, can distribute the parity. You had something else? Yeah. Same idea. Okay, that's called RAID 5. Okay, now you say I'm not going to keep a dedicated parity disk. I'm going to distribute the parity. Okay, so in my first stripe group, okay, D0 to D3 are going on the first 4 disks. The parity goes on the 5th disk. Okay, in the next round, I essentially put D4, D5, D6. I put the parity on the 4th disk, and then I put the data block. So you'll see that the parity is now spread, and you continue to do this. Okay? This means now, although every time you make an update to a block, I still have to update the parity block. The read, modify, write problem hasn't gone, but at least the parity disk is no longer a bottleneck, because it's not going to see a very high load. That load is going to get distributed across all my machines. Okay? This is called RAID level 5. Okay? Most of the disk arrays you will see on large systems by default will at least use RAID level 5. Okay? They might have additional techniques to address multiple disk failures, but this is kind of still a good way to configure a disk array. Okay? You essentially have distributed parity, and then you have RAID 5. Okay? Questions here? All right, so that's RAID. That was the first concept. Now, this has nothing to do with xFS. Okay? But xFS, remember I said you are going to distribute your files across all machines, has to use parity for that exact reason that some machine might actually crash, a disk might go away. Okay? So I need to keep track of parity. So xFS will incorporate RAID, and we'll come to that. Okay. All right. So this is all done. Okay. So xFS has this notion of a software RAID where you are going to take a set of machines, okay, and you are going to do what is called network striping. Okay. Network striping is just the same as striping in a disk array, but you store the first block on the file on machine 1, second block on machine 2, third block on machine 3, and so on. Okay. So each disk looks like each machine looks like a disk from a network striping perspective. In disk striping, all those disks are attached to the same machine. At disk arrays, you just plug in four disks into a machine and you make an array out of it. So your server just happens to have 4 or 5 disks. In xFS, if you remember what I showed you a few slides ago, yeah, so many machines, each of them has a disk. Okay, you are going to now stripe across the network because it's an independent machine, right? So block 1 goes here, block 2, block 3, then you keep a parity, and then you do the same thing. Okay? And you have to do this in software because you can't use a disk arrays use a dedicated hardware to do parity, but not in xFS. You have to do this as a software RAID. Okay? So essentially, that's one thing we are going to use in xFS. Okay? Use a software RAID and RAID level 5. Okay? The second concept that is used in xFS is also derived from another system. It's called log structured file system, or LFS. Okay? This idea was designed back in the 80s or 90s, a very old idea. Okay? xFS is a modern file system. It incorporates this idea. But let me explain what xFS actually means. Okay? So xFS is designed for a special case, just as Coda was designed for a special case, mobile computing. Okay? And not xFS, rather. Log structured file system, or LFS, is also designed for a special case. Okay? So what's the special case? The case is one where servers use a lot of caching just to improve performance. Okay? Caching is a good optimization in general to use, and file systems use it aggressively. Okay? So now let's take a file system, or a file server rather, that has a big cache. Okay? I'm going to make a small picture here. You see. Okay? That's my server. Okay? I put a cache here, and that's my disk. Okay? Let's say there is IO request coming to the server. Okay? We'll assume that the workload has some mix of reads and writes. Okay? For simplicity, let's assume that half the requests are reads and half the requests are writes. Okay? Whenever requests come in, okay, the server is first going to say, is that request, whatever is being asked, is that cached in memory or reads? Okay? If it's a cache hit, you are going to immediately take the cache data and return it. You're not going to go and read the data from disk, which is already cached in memory. Okay? So for read requests, you always check the cache, and if it's a cache hit, you are going to send that data back, and you don't have to read from the disk. Okay? Writes, on the other hand, always have to go to the disk. Okay? Maybe not immediately if you have write through and write back caching, but whatever you write has to eventually flow to the disk, because you can't just keep data in memory. If the machine crashes, the data is gone. So whatever you write eventually has to be persisted to either immediately or after some period of time, like NFS will do after 30 seconds. Okay? So that's how a cache is going to behave. Okay? So now from the file server's perspective, okay, what is coming in is a balanced workloads of reads and writes. Okay? And the workload is going to filter through the cache and hit the disk. Okay? The question is, what is the disk traffic going to look like when the incoming traffic to the server is a mix of reads and writes? How does the cache actually change that mix? Yes, in what way? So it reduces by half. Okay. So assume an ideal case where your cache is very effective. Okay. All the reads are going to be absorbed by the cache, because the cache is effective. Most of the reads are cached. So those requests are never going to be seen by the disk. Okay. Only the writes are going to filter through and go to the disk. Okay. So what this is saying is, in a modern file server where you have a large memory cache, even though the incoming request may be a good mix of reads and writes, the disk traffic is going to be predominantly writes and some cache misses which are reads. Right? Is that clear? Okay. So then the question is, if my not a file system, a disk system is mostly seeing a write traffic, how should I change it, okay, to optimize for a largely write traffic? Okay. Now, modern disks or all the file systems you've seen don't actually distinguish between if the request reads or write. They just store data blocks of the file somewhere. When you request it, you read the metadata, you read the blocks, or if you write it, you write to a location and so on. They're not optimized for any particular type of access. But here we are saying that modern file systems, because of the cache, we only pass writes to this. Okay, what can we do to improve write performance? Okay, yes, question.
Hold off and not immediately send writes. So instead of just doing the small writes, depending on however we're storing the data, that can be very expensive. Back several writes and doing it all at once.
Okay. One suggestion is don't write immediately, batch writes and write them out. Okay. That will improve performance or making lots of little writes. Okay. That's one idea. Okay. We'll use that one. Okay. But there are other ideas as well. And log structured file systems, since they were designed in the 1990s, predated solid state disks. So what I'm going to talk about here applies to more traditional disks, not solid state disks. Okay? What's a traditional disk look like? If you've seen a DVD or a CD, a disk essentially is a platter of these CDs. Okay? These disks are spinning, but you got to essentially go and read data from wherever it's stored on this platter. Okay? So typically the disk support random access, which means you ask for a write. If you think of a CD, it's going to just move to that location where it's recorded and it's going to read from there. Okay? And if you want to write to a location, it will move the diskette to where you want to write and write to them. Okay? But as I said, okay, our traffic is mostly writes. We don't need to worry about reads. Okay? So why bother trying to jump back and forth and trying to read and write from random location? Why not just write sequentially to disk so I don't have to move the disk head at all? Okay? The disk head is an overhead. It's called disk seek overhead. Okay? Seeks are slow because the disk is simply not doing anything. You have this platter just moving the head to the right location. While you're doing that, nothing actually is happening. You can't read or write. Only after you position the disk head at the right location can you read. Okay? Similar to if you actually played a DVD, which you may not have in a streaming world. But if you actually go and seek to some chapter on a DVD, that disk head on your DVD player is going to move to that location in that movie and then start playing it. Right? That's some other location from where it was. So it's going to wait, do a seek and read it. Okay? That's wasted overhead. Okay? And we don't need to worry about it here because we'll assume that everything is just mostly a write-only traffic. So we are going to write sequentially to disk. We'll start at block 1, and as writes come, we'll keep writing like a log. That's why it's called a log structured file system. You just write it as an append-only log. The next write goes to the next location, and the next write goes on the next location, and so on and so on. Okay? Now, if you update a block of an existing file, normally the file system would go and overwrite that block because they made a change. In a log structured file system, you go and append that new block to the beginning, and then you just mark that block somewhere in the middle of the log saying delete it. Okay? So you delete entries in the middle of the log because you still write to the, you append. You always write to the end of the log. Okay? This is going to vastly improve performance in the old style disks. Okay? None of this is necessary in solid state disks because solid state disks are no moving parts. Okay? Any location on disk can be accessed quickly without any overhead at all. So you don't need these optimizations anymore. But if you have the magnetic disk drives, this gives a huge improvement in performance. Disk seeks are minimized. Okay? Most of your work is useful work where you're continuously writing to the log. You never move the head. You just write to the next location, and so on. And that gives you very good performance. Okay? So this basic idea is called a log structured file system. Okay? So essentially the way you want to think about it is a file system is essentially now looking like a logical log where you keep just writing to the next location and so on. And as you update data that already exists, you're going to go and delete it, not delete it, but mark it as deleted from the middle of the log. Okay? So when you hit the end of the disk, you're going to go back to the beginning and start writing again, but you can't overwrite valid data. So you can only overwrite data that has been deleted. Okay? And so to do this, you have to also do garbage collection, because just as your garbage collection in Java, this file system has to do garbage collection, where it's going to take a set of deleted blocks and it merge them together. So one large chunk of empty space and then write them as a log. Okay? So one of the overheads is there are holes created where data has been deleted. And then since you can't, if you just write to each hole, then you are back to random access. You write here, then you jump to the next hole, you back to having seeks. You don't want that. If you garbage collect and collect a bunch of holes by moving data around, that's like disk defragmentation, you're going to get good performance. Okay? So log structured file systems are two concepts. To improve write performance, you write in an append only log. Even if you update existing data, you don't go back to where the data lives. You just write it to the end of the log and just delete the portion of the log. And then to make sure that these holes that you have created are not going to result in random writes again, you are going to occasionally do garbage collection where you move data around and have a set of holes be joined so that you have one big chunk that you can write again as a log. Okay? And that is basically, those two ideas are going to give us very good write performance, because we don't care that much about read. There will be occasional reads that will be random access, but that's okay. Most of our IO is now writes. Okay. Yes, question. Okay, good question. The question is there an overhead to maintain the lookup, because you need to keep track of where the blocks of the file are. So you, every time you update the file, you have to update the inode or the metadata. Okay? But in this case, if your metadata is stored on a known location, that's a disk seek. So you have to go back to the super block to update it. So even metadata is written in the log. So you need to have additional data structures to first figure out, if I access the file, where is the metadata? And then once you have metadata, you have to ask where are the blocks of the file and so on. So there is higher overhead. That's a short answer, because you are trying to improve write performance. So you don't want to go back and overwrite something. Every time you do a write, you just write it to the end of the log. So I never have to go backwards. And that's the basic idea. That will improve write performance, but it will also create higher lookup overhead, because you keep moving where the contents of the file are, you keep moving where the metadata is, and so on. Yes, question.
Why would cache is right, come as free one.
Okay, question is, there's an alternative approach where you are going to take writes, cache them, and write them as 1, 2, 3. That is in fact what the log structured file system does. Reads are directly cached, writes are put in the cache, you batch them. That was the idea that was mentioned earlier, and you write that entire batch as a append only log. Okay, so you take a bunch of writes and you just write them as one large chunk. And you take the next set of writes, you write them as another chunk, but you append to the previous one. So you keep writing sequentially on your disk. Okay. Yeah. So LFS, the question is LFS one server. So log structured file systems are designed as a single disk system. Okay. Here we are talking about it in an xFS manner. So we are going to combine both. Okay. So here is our log. Okay. We are going to take that log and we are going to stripe it on our machines. Okay. These are machines in my xFS system. They're shown as disks. These are disks on independent machines. Okay. So I take this log segment. I essentially partition it into a stripe group. I compute a parity. So I take this entire stripe. I put the first fragment on this machine 1, okay, or this one, and second one here, third one here, and fourth. So I combined RAID 5 striping with a log structured file system. So in xFS, it's no longer a single disk system. Original LFS was entirely a single disk system. Okay, so I'm still trying to achieve sequential writes, because the next segment is going to write sequentially to the next location on this disk 1 and disk 2, disk 3, and so on. So that's the reason you have LFS at all. But I combine these two ideas. Okay, yes, question.
I guess my question is, case of the manager fails.
Yeah, the question is in a normal RAID, not in XFS, you have a hardware RAID controller which keeps track of data blocks parity. What happens if the RAID controller fails? The RAID controller fails, then you have problems because you won't get access to the disk because it has information. Now you can plug in a different card, and so long as the configuration is same, it can still get things, but that can be a point of failure, right? Yes, and if you do software RAID, you don't need to worry about that because there's no controller. All of this is XOR stuff is happening in software. It's slower, but there is no single piece of hardware. In XFS, there's no hardware because your file system is spanning multiple machines. So you can't do all of this in any one machine anyway. Okay, all right. We have just 1 minute. So I'm going to talk very quickly, introduce HDFS. So this is the distributed file system that is associated with the Hadoop file system. If you're done MapReduce or done Spark, if you've taken the distributed data something course, processing course, I think 500 level course, you probably encountered HDFS. Even if you haven't, don't worry about it. So we'll talk about distributed data processing next time. So what HDFS does is it is a file system designed for large data sets. Okay? Normal file system optimized for small files because most files are small, some files are large. In HDFS, it's designed for large scale data processing. So you assume that files are very large. Okay? So this file system is optimized for large files. Okay? Just as Coda was optimized for mobile computing, xFS or log structured file system is optimized for a file server with large cache. HDFS says all files are going to be by and large in this system because you're doing large scale data processing. So I'm going to essentially optimize for it. So what does that mean? Okay, so you're also going to optimize the file system for batch processing rather than interactive. Okay, this file system is not going to work well. You open the file in an editor and start editing it. That's interactive processing. Okay, it will work very well if you want to access 1 gigabyte of data all at once to process it. Okay, but it's designed for that model, not for interactive processing. Yeah, large scale data sets, this can scale to hundreds of machines. The assumption here is because it's a data set, you use what is called a worm model. Worm essentially means write once, read many. Okay? You create the data set once, maybe it's a machine learning training data set. It's going to just sit there. You might train lots of different models with that data set. Okay? So you're going to read it many, many times, but you don't go and change some image in a data set or something like that. Right? So that's the data set model that you're going to essentially use. And you're going to also say that most likely I want to move the computation to a machine where the data resides. So don't have to move a lot of data over a network in a cluster and so on. Okay? So very quickly, and we'll continue this next time. The principal idea here is that there are multiple servers in the system. Okay? Some servers are going to be called metadata servers, and some machines are going to be called data servers. The whole purpose of a metadata server is it keeps track of where the data blocks reside. Okay? And the data servers are actually going to keep copies of the data of this large file. Okay? That's one. The second thing is everything is replicated. Okay? Because disk can fail, machine can fail. By default, replication factor is 3. Okay? You're not using striping. This is straight like mirroring. Make 3 copies of the file, store it on multiple machines. Okay? Because they say disk space is cheap, so why bother doing striping? No need to do all that. Forget 2 copies. Let's keep 3 copies. Okay? Even if 2 machines fail, my file is still available. Right? So different design decision. Okay? Separation of data from metadata, large scale replication. I shouldn't say large scale replication with factor of 3, just to avoid any data loss. Okay, let's continue this next time because we ran over time, and then we'll see what else this system can do.